Yes, because it's and when I was at UNC, we would we would we could not schedule meetings, and we could not schedule meetings early on the day, like so today, like the day after. You also, there was no point in giving an assignment that was due today because no one would do it. I had one professor who would love giving tests the day after, but aside from him, generally the entire school recognized the fact that nothing really happened the before noon on the day after Duke Carolina games, because either we won and everyone was up late, or we lost and everyone was drinking because they were depressed. And so we can talk more about Duke Carolina basketball later, and we will. So let's talk about 2-3 trees. So 2-3 trees are not binary trees. They are trees, but they are not binary trees. And the biggest thing which stops them from being a binary tree is that a parent can have more than have 3 children. Since binary has no sense of 3, I guess it does really, but it doesn't know. It doesn't really know about 3. In fact, that's 2. There were zeros and ones everywhere. I thought I saw a 2. There's no such thing as a 2 vendor. Anyways, so we can have up to 3 children. And 2-3 trees, in order for it to be a 2-3 tree, it has to satisfy these properties. And we talked about this with the binary tree the other day, where Rob, you asked about how does it know how to search if things are out of order. And my answer was, well, that's not a binary tree, which is really a cop-out. But what we do for 2-3 trees is we establish a set of properties, and we can do insert, search, and delete. And these things will only work on objects which are 2-3 trees. This is predicated on the assumption that our insert and delete will also, every operation that we can do with those, will generate a new 2-3 tree. And so we'll use 2-3 trees to maintain other new 2-3 trees. And so 2-3 trees have these properties. The first one is that the node size property, which is that every internal node has at most 3 children and at least 2 children. Now, when I talk about internal nodes, again, keep in mind I am not, there's my marker, I am not talking about so those are the internal nodes. Those all have 2 or 3 children. In this case, they all have 2, so that's great. These are the leaf nodes. Those have no children. So that's perfectly cool. We have the depth property that all leaf nodes have the same depth. So that means is invalid. It's invalid because you have leaf nodes right here that are lower than that leaf node. This is a nice marker. It's the best one yet. We have an order property, which is that internal nodes that have 1 value have 2 children. And everything to the left is less than V, and everything to the right is greater than V. You might ask about equal to V. Well, I've got news. I am going to entirely ignore equals to in these discussions. I'm doing that because it becomes really, really painful to try and work out all the subcases for if things are equal to, how you break them down. And you can figure it out on your own if you feel so inclined to, but it's just really a lot of extra work for very little gain in the type of thing that we're doing here. You can figure it out after the fact. We also have an order property too. So in a binary tree, every node had 1 value. In a 2-3 tree, that's not the case. You can have tree elements that have 2 values associated with them. If they have 2 values associated with them, then they have 3 children. So the example I give, so I can have 1, 5 as 2 elements in there. Then you have 3 children, left, middle, and right. Every child and every element that's of the left tree has a value which is less than 1. Everything which is in the middle has a value greater than 1 and less than 5. And everything on the right hand is greater than 5. Everyone cool with this?
With 5, if there was another 5, it would go in the middle.
Remember, we're ignoring. There are no duplicate entries.
Oh, okay. They're not.
No, not even it. The way you end up solving that is you basically have to make. This is why it becomes annoying. Is you have to make a decision. Like, do equals always go? Where do they fit in here? It also becomes annoying too because if you allow for equal elements, what happens if you have 5, 5? That means you have a middle tree in here of just 5s. So these subcases can be worked out, but basically you make a decision. Do equals 2 always go to the left side, or do they go to the right side? So if we were doing it, we'd probably do something like that. So if it's equal to 1, it'd go here. If it's equal to 5, it would go here, and then that would be strictly greater than. Or flip it the other way around. Plus, we have to allow for the possibility that we can have the same element in both of those, and we have an entire subtree just of that element. We can do that, and we can work out the subcases, but it takes a lot more time, and it's not. It's more of a side issue. But that's why we ignore it.
So what can that middle one be?
What?
What's the middle one?
The middle one is every element between 1 and 5. Any questions? So let's talk about the height of the 2-3 tree. We have a theorem that the height of a 2-3 tree is order of log base n. And so this proof is not terribly hard. So first let's let h denote the height of the 2-3 tree. So we want to show that h is an element of order n. Since there are at least 2 to the I elements at depth 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 blah. And no items are at depth h plus 1. That means that the total number of elements that we have in the tree is equal to 1 plus 2 plus 4 plus all the way up. And so that means that the number of elements is equal to 2 to the h plus 1 minus 1, which is the summation of the series. So that means that h is equal to order log n through using logarithmic rules. This proof is not, it relies on the idea that we have at least 2 elements in here, and the tallest our tree will be is when there are the fewest number of elements in each level. So 1 element in the top level, 2 in the next, 4 in the next, 8, 16, 32, 64. And that's what we're summing up here, is sort of the minimal number of elements in each one of the levels. 1, 2, 4, 8, 16, blah, 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 blah. Because every tree has to be, all leaf nodes have to be at the same level. We know everything has to be completely filled out if the tree is of that height. So if it satisfies the properties beforehand, this represents the maximal height of the node that we can have for that particular set of elements. And so that gives us a big O. Does that make sense? It's similar to, it's basically the same proof that we use for binary trees as well. So let's talk about 2-3 search. Fun in a bun. So we have at the top there, search, the primary, we have 2 different notions of search. So our primary search starts with a particular node, and we're searching for a value. Again, if we have the root, then what we're searching for is we want to make sure that the root will be the node that we pass in there, or n, and the value we're searching for will be the particular value that we want to find. If that node we are looking at is a 2 node, then what we do is we do search 2, and we call this method. If the node we're looking for is a 3 node, then we call this search. Let's do an example. sheet. So, these are nice. I'll make sure to use that notes up there. So, my root has 10 and 15 on it. He has a child 2 and 8. Has a child 12, and then has a child 18. Let's actually add a couple more nodes to here so we can have a little bit more interesting search going on. We'll have 11, 13, and then 17, 420, -1, 5, and 9. This marker's great. It's a shame that it'll dry up and die. Circle of marker. Okay, so let's try and find the element 13. Lucky 13. It has to be someone's lucky number. And yeah, it has to go somewhere. I mean, yeah, luck. I mean, luck is cumulative. I mean, it's luck can neither be created nor destroyed. Isn't that one of the laws of intraluck? Okay, so that's our node that we're starting off at the top. So is that a 2 node or is it a 3 node? It's a 3 node. Now, keep in mind, it's called a 3 node because it has 3 children. And it was like, I'll accept that it's a 3 node because it seems to have more than that. But that confused me when I first learned this. So it's called a 3 node because it has 3 children. We call search 3. And so search 3 nodes have 2 values associated with them. Value 1 and value 2. Is it equal to value 1? Is it equal to value 2? Nope. So then what we do is the value 13 less than value 1?
So in this, though, the n would be the root node, and the v would be the value we're searching for.
N is the current node we're looking at.
The current node we're looking at.
Yeah. So it's a recursive algorithm. So we call it the first time with the root. Actually, I'm going to make one change to this tree. Instead of this just being 420, I'm actually going to make it 420 and 1138. I'm going to do that, and that'll be important later on. It's not just to put another funny number in there. What I wonder is how many people who have actually seen 1138 after, like, yeah, but you saw it before you heard me talk about it in class, so that's cheating. I don't think anyone has ever actually seen it, despite me using that number in literally every class I've taught. That and the movie Sneakers. Anyways. So, 13, the node we're on, 10, 15. It's not less than value 1, so is it greater than value 2? No. So it fails that if, it fails that else if, so now we're in the else. So, first what we have to do is say, is the middle node, so the tree that it connects from, is that equal to null? It's not, there's a node there, so we can progress down it. So now what we do is we do search on 12. And so now we go back up to the top and say, if a node is a 2 or 3 tree, is this a 2 tree or a 3 tree? A 2 node or a 3 node? 2 node. So we say, is 12 equal to 13? No. Is the value less than the value that's in here? No, it's greater than it. So what we do, check to see, does it have a right node? Yes. Progress down there, call search. We call search again with this node. Is it a 2, 3, or a 2 node or a 3 node? 2 node. And leaf nodes are still 2 nodes. If they have 1 value, it's still a 2 node. That's the reason why I added this over here. This is a 3 node with no children. Which makes
it has 2 values.
It's a 3 node. If there's 1 value, it's a 2 node.
But doesn't 7 Is it 78 or 78?
Where?
Right above 420.
18.
Oh, okay.
It could be 78 too. It actually wouldn't. Yeah, it would actually still work if it was 78. But 78's not funny. Now can't do that. 18's really not funny. Okay. So now we're still over here. We're at 13, and we say, okay, 2 node or 3 node? It's a 2 node. So now we say, does this value equal the value we're looking for? Yeah. All right, and we return this node. Yay, we successfully searched. Okay, let's do 1138. Okay, start up at the top. 2 node or 3 node? 3. 1138. Which division is it in? It's greater than 15, so we end up going down this node. 2 node or 3 node? 2. Greater than 18? Yes. Okay, now we're finally at the part where it's different. Now we're over in this node, 2 node or 3 node? 3 node. Is it equal to the first value? No. Is it equal to the second value? Yes. Return this node.
But you return 420.
Return the entire node itself. You return the entire node itself. You can return, depending on how your value is set up, it is possible that you could just return the value, but return the entire node is probably a safer activity. And then what I would probably do is I would have a wrapper class around this. So this, I would have a 2-3 tree node, and these would be all internal methods. And then I would have my other search, which would be exposed as through the priority queue interface, which was just search for student or search for ID. And that would manage actually pulling out and getting the student from there. But the internal stuff here would return the entire node. And then,
Is there a relationship between the nodes that have 2 values usually?
the only relationship is that one is less than the other one. That's the only relationship.
But if you returned 420 and 1138,
You
and
return,
you deleted it,
you can't delete a node. You can only delete a value, and that's what makes delete so extra spicy fun. Is that you don't delete nodes in here, you delete values. And so what happens here, if you delete 420, this is easy. Deleting one value on a 3 node here is really easy. Becomes a 2 node 1138. That's not so bad. Where it becomes a problem is delete 15. That's why you're not doing it.
that makes sense.
So there's no default search method for binary search trees or 2-3 trees?
What do you mean?
Well, you had to make your own search method.
Yes, you have to do that for binary trees too. At some level, someone has to make it.
Okay.
Yeah, so
It just seems like if it's a binary search tree, they'd have a search function.
no, but since you're also making the tree itself.
Oh, okay.
Yeah, so when you look at the linked list, you'll notice that I actually made my own linked list search method in there as well, because even though I'm using a very standard data structure, because it's my linked list, I have to make my own search for it. So because you'll be making your own binary tree from scratch, that home cooking requires you to make your own home cook search method as well.
So if that 3 node was like 0, 1, 3, what would it be?
If this was what?
Like 0, 1, 3.
You would not have that in this tree. And so you would not have that because this tree has no place for 0 and 1138. That would not be a 2-3 tree because that would violate the property that everything that's right child is greater than it. So we need insert to make sure that stuff doesn't occur. Any questions about this? This one is very similar to 2-3 trees. I mean, to binary trees, with the only thing of you have these occasional excursions down the middle. But it's not terribly different. Where we start stuff becomes odd is when we start getting to insert. And delete becomes extra odd. So, insert. First thing we do, because we're not allowing duplicates, what we do first is we search the tree, see if it exists. If it doesn't exist, if the value's in the tree, we're done. We're like, oh, you're trying to insert something which is already there. I had a boss at Microsoft who used to say that you can only fire someone once, so make it a good firing when you do. We had a really, really, really incompetent coworker who got fired, and we found out later he was doing another job on the side, which violated his contract. And we brought it to our boss's attention about what's going on. He's like, "You can only fire him once. What are we gonna do? What are we gonna do?" So
What did he do?
nothing. There's nothing you can. I mean, you can sue him, but it's not worth the effort generally to sue someone. You occasionally see major CEOs getting fired for violating their contract clauses, but honestly, it's almost never worth the effort. It's only if a company is hemorrhaging money and someone looks like they have a lot of it that they'll actually sue that other person. Usually, it's easier just to be like, shake your hand like Wile E. Coyote, and then go on with your day and complain about him for the next 5 years.
Yes. Wouldn't have
Yeah. Yeah.
It sounds like there's a market for revenge for companies.
There is.
Bring them up before
I'd like to exact revenge on this coworker, but not cost much. Can you do something for me? So yeah. So anyways, so just like you can only fire someone once, in this list you can only have one node in here. So how do we tell if it, so the search, how do we tell if it fails? Going back to the search quickly, if we were looking for the element 14, what would happen is we'd look in the top and say, oh, is it between 10 and 15? Yes. Is it greater than 12? Yes. Oh, is it greater than 13? Yes. Does 13 have any children? No. 14 can't exist. Return null. And so that's, you would do the search first and be like, oh, it's not in there. So
to check that, you just be like, if search equal null.
And on top of that, what you'll actually want to do is you'll want to have search equals null, and you actually want to be aware of what is the last value. So we're not going to entirely, we're going to actually, our insert is not going to call search entirely. It's going to have search built into it because we want to do a little bit more. We want to find where it would be,
So you can just go ahead
and then keep track of what we would do. And so we actually have this really cool thing that, so if we wanted to insert 14 in here, I hope this blue is as good as the black. It's gonna let me down, I just know it. It's not so bad. It's because of Jay Lee, hammer hand over there. He's like, the markers don't work well, so I hit them harder on the board.
Carrie has her own markers.
Yeah.
She's like,
Yeah.
oh, I forgot my markers.
She has quality markers. I'm a cheap man. I'm not made of markers. So we have, if we want to insert 14, we search the tree, find 14. Doesn't exist. Fail. What's the last node that we try to insert it at? This 13 node. We have a really cool thing that we can do in this case where the node that we wanted to insert to was a 2 node. All we have to do in that case is we make it a 3 node and just add 14 to it.
So you don't make it a song.
Not in that case. Not when it's a 2 node that had. If it's a 2 node, if you have a 2 leaf node where you would insert it, you just make it a 3 node, and then you're done. Where life becomes a lot more complicated, like it's like great, it worked once. Where life becomes a lot more complicated is suppose I want to insert 14.5. I really should space these numbers out better. Suppose we want to insert 14.5 in here. What do? The solution is insert 14.5, and then you're like, oh, this now violates our 2-3 tree property, and it does. So after we insert 14.5, the police detect that it's coming along, and we have to fix it up before they catch us. So we've created an illegal node, and the rest of insert is about fixing up that illegal node and making it so that we don't have any nodes in there with more than 2 values. So let's go through some examples about, let's go through an example that I have on the slides about how to do it. So we have, we want to insert 7 into a tree that contains the elements 5 and 6. So what do? We illegally insert 7 into the node. Now, this is an illegal node. Does anyone have an idea of how we should fix this?
Make 7 a child.
What?
Make 7 a child.
Make 5 and 7.
Yeah, what we do is we split out 6 and make it its own node, and then we take 5 and 7 and make them both children of 6.
So you take out the middle.
You take out the middle element, and then you make its 2 children an element.
So, is there a particular reason you don't just add 14.5 to the middle node and just be done with it?
The reason why you don't do that is because in this case it actually works out pretty well because this is a 2 node above it, and that's the case we're going to step through in the next slide. But what happens is it becomes a little complicated once you start having these nodes that are densely packed, and you start having lots of 3 nodes in there. You don't actually ever have to create the illegal 2 node because you don't have to. We create it for the description of how to do it because it makes it easier to do. If I were writing this up, and you guys are, I probably wouldn't create a new class for node and then have it fixed up. I'd probably just keep track of the fact that you've temporarily, you're in a situation where you have an illegal set of elements, and then you're breaking it up and making new ones. Does that make sense? Because it becomes a lot easier to describe like this, but a lot harder to code. And that's often the case with pseudocode. We write pseudocode because it's easy to describe, even if it makes it more of your life difficult when you code it up. And you're like, I hate you so much right now. Sean looks like a man who spent last night trying to get merge sort working.
No.
Yeah.
Is there any benefit to iterative versus recursive?
Yes. Do you want to know what that is? Or?
What?
So the question, future you, is there? I should be doing that because you actually cannot hear anyone's voice aside from mine. So it makes it look like I'm a crazy man when I put on these videos. So the question that Todd asked, was, is there any different advantage to iterative versus recursive? The advantage that iterative has is that iterative does not need to maintain the method call stack that the way merge sort is written does. And so that, even though it maintains a stack, the call stack, which is the series of methods that you call, actually consumes a lot of memory. And so if you have really deep calls, then you can actually run out of memory sooner with recursive than you will with iterative.
We were trying to program iterative and it kept changing it into it almost changed into like bubble sort, right? Where we were trying to do it.
We messed up.
Yeah. It should the time complexity should be on par with recursive. They are about the same for what you guys will do. The difference is really about memory. Time-wise, they're about the same. Some systems, some compilers can optimize better for recursive. Other ones can optimize better for iterative. But yeah. So if it's looking like bubble sort time complexity, and you're using built-in arrays for both of them, or array lists for both of them, then you are doing something wrong, especially at 10,000 elements. But interesting sort should be faster. But anyways, let's get back to talking about this. So that method had a problem that it assumed that nothing was above it. That was our entire tree was 5 and 6. So now what we need to do is we end up creating a new root node here and then creating 2 subtrees beneath it. What we want to now, if we have a tree where we have 1, 2, 3, 4, and we want to insert 5, we find the place that it would be inserted, 3, 4, 5. And now what do?
Make 3 and 5 the child of that node.
Of the node, you're close. Which one?
Of the 3 node at the bottom, or to the right of 2, or 2 is right child.
I think you're on the right track. What we do is we take 4 and bring that up a level, turn the 2 node into, God, that's confusing. Turn the node containing 2 into a 3 node that contains 2 and 4, and now make it so that
Should have used 1138.
what?
Should have used 1138.
I really should have used 1138. Now we make it so that now we take the left-hand side of our 3 node and make that the middle node here, and take the right-hand side and make that the right of there.
Why can't you just leave 3? Oh yeah, it's not.
Yeah, because this violates the property that this needs to have 3
Yeah,
children.
It's not bigger.
Okay, so now let's insert 5 into 6. Okay, that was easy. Woo! Insert 6. What do we do? Bam! I love that. Okay, now let's insert 7. So now what do we do?
So 5 becomes left node and 7 becomes the right node.
So 5 becomes what?
The left node is 6.
Yes, will we bring 6 up?
Yeah.
Bringing 6 up makes an illegal 4 node up there. So before so now we had this illegal 4 node, 1, 3, 5, 7.
Can you make 6 stay down there and move 5 and 7 down?
Made what?
Yeah, you can leave 6 right there and move 5 and 7 down.
No, because then that would violate the property about all leaf nodes being at the same level.
Oh yeah, you can have to.
Couldn't you move 5 up and put 4 down into 3?
That becomes a lot more confusing, but yes, technically that would work. So we move 6 up. We make that a 3 an illegal 4 node. We then make 5 and 7 children of the illegal 4 node. But now we have an illegal 4 node. And we know how to fix that. We bring the 4 up and turn the remnants of the illegal 4 node into two nodes, and it becomes like this.
That's also confusing.
The thing is, it may be confusing, but it's systematic. You're like, I can't wait to program this.
Well, is it doing the same operation every time?
Yeah.
Like up, over, left,
Yeah,
straight, whatever?
yeah. And so this is the pseudocode for it.
Whoa.
Well, this is not. This is the pseudocode for students.
This is cool.
You notice that I get kinda brief.
I was just gonna say, you get so lazy with the variable names.
It's not that I'm lazy. It's that if I made them longer, they wouldn't fit on the screen.
Speaking to slides.
No, it's cheating. Alright, 2 nodes have left and right. So let's go over the terms because that's what I assume you're going to want when you actually go back and look at this. If A is a left node, it has left child, right child, and value. So A dot B is the value, A dot L, left tree, A dot right, right tree. 3 node. And they also have A dot P, which is their parent. So you have to keep track of your parent, your left, your right, and your value. 3 nodes have A dot left, A dot right, and A dot middle, which I actually do get lazy on this one, where I start using it as dot M. Rather than calling it dot middle, because that was too helpful, I also refer to it as dot M throughout here as well. Three nodes also have value 1 and value 2, which is V1 and V2. The legal 4 nodes have value 1, value 2, value 3, left, right, middle 1, and middle 2. So let's write this up on our handy dandy guide.
Wait, what's P?
Okay, so I'll write these all up. Does that sound good? So you're not crying. Alright, I'll use the good marker for this one. Okay. This is a 2 node. We have, and we'll call this node A. The value here, A dot B, is the value. The left child, A dot L. Right child, A dot R. The parent is A dot P. Three nodes. A dot value 1, A dot value 2. That's J Lee.
Julie?
Not J Lee, that's
Andrea. Oh, no.
who's in there?
Is it elementary?
It might be Andrea, I don't know.
I know it's a calculus one class.
It's
Calculus 1?
There was a calculus one class that
Yeah.
was
Yeah, it's probably Andrea.
at the same time as this one, so.
They do so much more writing than we do. Here, the children of this one are A dot right. Sorry, A dot left. You're like, what the hell are you doing, Aaron? A dot right, A dot M, or A dot middle, depending on how typey I'm feeling. The 4 node has A dot value 1, A dot value 2, A dot value 3. A dot left, A dot right, A dot middle 1, A dot middle 2, and then A dot parent. Note in here, you have things N dot P dot P. What do you think that refers to? Your grandparent. It's at the top of the second column here. N dot P dot P.
Oh, X.
Wait, so that's supposed to be the parent of the
In
parent?
parent, nodes parent parent. So N's parent parent. This is the split. This is the method that's used for correcting 4 nodes and putting them into 2 nodes. So this is the complicated part of it.
Didn't earlier you say that we weren't going to make a 4-node class?
It depends. So I wrote this with a 4-node class because it was easier for me to do the pseudocode that way. I don't know. I mean, and so for pseudocode purposes, this was easier. Implementation purposes, I don't know if I would create one. Because if it's easier for you to follow the pseudocode as closely as possible, then you could go and create one.
Yeah.
I probably wouldn't create one simply because I think it's easier for me intuitively not to have those extra classes. But you can do it either way. It's easier to explain the pseudocode and the description with them, but in an implementation sense, I think it'll be easier not to have them. So. Because you see, they get created and they die immediately, and that's what ends up happening. Is
That would just be
yeah. And now, I mean, split is something that we do call. This is for correcting 4 nodes, and so you are calling it on a 4 node that you've sort of created. So it depends on how you want to manage that. Either way works. So insert. Here's the algorithm. Search the tree. If it fails, then figure out what the last node in there is. If it's a 2 node, then just turn it into a 3 node. If it's a 3 node, then make it into a 4 node and add the value into the appropriate place, and then call split on it. So call that other algorithm to fix it up, and split will fix everything up all the way to the root. One note for when you implement this, you can't just use the search as we've had there, because search returns null if you fail. So you have to do something more. You don't want it to return. You have to be careful about what you actually return, search, and how you write that up. You either write your own search from here, which is copy and paste, or you need to do a little more clever version of search. A slightly clever implementation of search can get around this problem, but I'll leave it up to y'all. This is the reason why you return the entire node for search and not just the value. So we're out of time for this. We'll go through the analysis of this. Is it takes log n. Takes log n because search, and then that I'm just giving you the split takes log n because you could worst case go all the way up to the top and then log n. We'll talk about how to delete next class. I'll post the lab for this afternoon. The pseudocode, I believe, the code for linked list, I believe, is already posted. But
Yeah, Bob, what's going on today?
yes, I do.